because when you have a table, is fairly long, and when you want to carry a table, if you lift a table from one side, what you will achieve is turning the table rather than carrying it. And when things turn, physicists teach us that moments, it's called something moments, come in. And this moment is no more just the weight of the table. It is the weight of the table multiplied by how far away from you it is acting. And that's why when somebody else carries it from the other side, you have now contained that distance into the center of the table, and the two of you are able to carry it. What I'm trying to say is that in nature, it is not always so that the summation of component efforts will be equal to the resulting efforts. There are always contexts that bring about a much greater result. The result will always be greater than the summation of the efforts that are put in. So when we say a system is a collection of many parts, each of them acting on their own, but adding together to produce much greater result than you would have expected if each of the parts was acting on its own. This could be a mechanism, for example, when you look at gear systems, you see wheels, turning wheels. You have very many wheels put together with gear teeth such that one has a smaller radius than the other and one is turning. And you find that network of gears does things beyond which each of those gears will do. And that is the basis of everything we refer to as machine. It is necessarily a system. And that is why a car, something that otherwise is a body. I mean, if somebody made a car of wood, put wheels, put tires, put everything that you have in a car, make it of metal, and you do not build in mechanisms that act like a system, it is just a showpiece. It just stays there. Nothing happens. But once you start looking at the individual contributions of various components, and you start arranging these components together in such a way that one aids the other to achieve results, then you find that the overall result is much greater than what each of these can achieve. Let's just imagine the idea of the gear system of a car. You know, when you are driving a car, well, these days we hardly drive manual shift gears, but in those days, you start the car because it takes a lot of effort to make something that it's at rest to move. You start with gear 1, and that gets the car to move. If you try to start the car with gear 4, the engine will stall. That is because the system that has been built there has a way of behaving in gear 1 which it does not behave in gear 4. So once you put the car in gear 1 and you are able to move the car, you have now overcome the resistance of the body from moving from rest. Then you can change to gear 2. If you do not change to gear 2, you find that the car will start making a noise. The car will start complaining that I have discharged the responsibility you gave to me to get this thing moving. Now, to keep it moving. I don't need to be making this much effort. So you change to gear 2, and you change to gear 3, and you get into gear 4, and some even have up to gear 5. So, this is the essence of systems. Elements, components put together, each of them contributing something, sometimes so small, almost insignificant. But when these components come together, then you see a much greater result than you will have expected from each of the components. To get a better understanding of this thing about systems, let me talk about something a little philosophical. We talk of a duality or a dichotomy of holism and reductionism. Holism, you can guess what it means, looking at things as a whole. And reductionism, looking at things as reduced. Sometimes we feel that if we break a system down into its component parts, that's what we refer to as reductionism. You reduce it to the component parts. Our gut feeling is that once we understand each of the parts, each of the components, then we have understood the system.